Hi, in this video we will do some examples in which we need to show a given matrix is diagonalizable and find the invertible matrix P and diagonal matrix D such that P inverse A, P is D. Well, first recall that an n by n matrix and matrix A is diagonalizable if and only if it has n linearly independent eigenvectors. In other words, if we have a v1 equals to lambda 1 v2 v1, and then a v2 another lambda 2 v2 up to a n vn lambda n vn, such that the set v1 up to vn is linearly independent. Well, if that's the case, also we can see what is P, the matrix P, the invertible matrix is you put the eigenvector of lambda 1 in the first column, then v2 in the second column up to nth column, and the eigenvalues lambda 1 in the first 1 entry, lambda 2 in 2 entry, and lambda n to n entry. You have to note that I am putting exactly in the same order as the eigenvectors, the eigenvalues, okay? So this way we find PD, well, and these guys are exactly the invertible matrix such that this equality holds. Okay, let's see this in some examples. Well, first of all, this guy, eigenvalues. We have to find eigenvalues and eigenvectors, yes. Eigenvalues here, well, we just find the determinant of a minus lambda I, which is -7 minus lambda, and then it is -6, 8, 7 minus lambda. From this you get minus 49 plus lambda squared plus 48, which is lambda squared minus 1. From this you get two eigenvalues, 1 and -1. Very nice. So this right away tells me that the diagonal matrix is going to be of this form of 1, 0, 0, -1. Now, I want to find eigenvectors for lambda equal to 1 and eigenvectors for lambda equal to -1. Well, you do the work you need here, yes? -7 minus 1, -6, 8, 7 minus 1, 0, 0. We have to solve this. Right away, you do row 2 plus row 1. This will give us 0, 0, 0, and this was -8, -6 is 0. From here, you see that x is -6 over plus 6 over -8 times y, and y is a free variable. In other words, well, let me just put this there. The eigenvectors of this guy is going to be 6 minus, well, we can do better here. Yes, we can simplify, right? -3, 4 t and t here. For any non-zero t, you will get one of these. Just to get better values here, I can say that, okay, well, I can put t t equal to 4, for example. Yes, well, this one, if t is 4, then we have eigenvector negative 3, 4 is an eigenvector of lambda equal to 1. How about negative 1? You do the same works, negative 6 plus 1 this time, negative 6, 8, and then here 7 plus 1, and 0, 0. This, well, you do the work you need here. This is, I guess I can do negative R1 over negative 6, or just this, plus times 8, add to the R2. This will give us negative 6, negative 6, 0, 0, 0, 0. And from this, you see that x is negative y, and y is free variable t. So we have negative t, t, and from that you pick any values of t. So here I'm going to pick t equal to 1, which gives us negative 1, 1 is an eigenvector of lambda equal to a negative 1. Okay, now that we have both of these guys, it is easy to check that these two vectors, which are both eigenvectors of this matrix, are linearly independent. Well, there's a good fact on this, that these are eigenvectors of distinct eigenvalues, so this will be linearly independent. So right away from there, we know that matrix is diagonalizable. So A is diagonalizable, and the matrix P, D already we found it here. Matrix D is, well, first one is 1, so I have to pick an eigenvector from this one, negative 3, 4, and eigenvector of negative 1, which is this. And that is enough. That will give us what we have. For the second part, well, there are a lot of computations here. I will just do quickly write down some works here. So for this one, eigenvalues are lambda equal to 1 and 3. For lambda equal to 1, well, you need to solve, remember, a minus lambda, here is 1, I, 0. And from this, you will get two parameters. The solution will be of this form, that you have a 0, well, s here, t here, and then s here. In other words, we can write this as t 0, 1, 0 plus 1, 0, 1 times s. From this, you see that these two vectors, 0, 1, 0 and 1, 0, 1, is a basis for E1. So these are two eigenvectors from E1. For lambda equal to 3, you can do the same things, a minus 3i this time. And from that, you will see that the solutions for this guy is going to have 3 t. I'm just doing very special case of that, so will be minus 2, 2 is an eigenvector. Now, I found two eigenvectors for lambda equal to 1, which are linearly independent. And since this guy is eigenvector of different eigenvalues, so this, if I add to that list, these will form linearly independent set. So as you see, This is a set of vectors which are linearly independent, and from there you can conclude that A is diagonalizable. And well, how do we find D? You may say that, well, we have only two eigenvalues, but here I have to put three numbers because it's 3 by 3. 1, 3, and well, how about 1? Well, if you see here, this guy, if you find the characteristic polynomial, you notice that lambda equal to 1 has algebraic multiplicity 2. It means that I need 2 ones there. And you can see it even here that E1 has dimension 2, so you need to put 2 ones and 1, 3. How about P? Well, you do put your corresponding eigenvectors. These two first columns needs to be eigenvectors of 1, which can be in any order you like. So I can put this one and the other one. Also for the other, the last one, eigenvector of 3, which is 3, negative 2. Well, you can check now that P inverse AP is equal to D. Well, these were some examples that shows you how to find those P inverse P inverse P and diagonal matrix D, and show the matrix is diagonalizable.